Hello there, and welcome. You found your way here at just the right moment, or perhaps at no particular moment at all, because time, as we'll discover tonight, is a far more flexible and forgiving thing than we usually give it credit for. Wherever you are right now, whatever kind of day you've had, whatever thoughts are still quietly circling in the back of your mind, I want you to know that you are exactly where you need to be. There is nothing to do now. There is nowhere to be. There is only this. Tonight we're going to travel together through the universe. Not the urgent, dazzling, fast-moving universe of science documentaries, not the one with dramatic music and breathless narrators warning you that a star is about to explode. No. We're going to move through space the way light itself travels across the deepest, quietest parts of it. Slowly, steadily, without hurry, touching each remarkable thing we find along the way with patience and wonder. Space has always been with us. Every culture that has ever existed on this small warm planet has looked up at the same sky. Ancient shepherds lying in the grass of Mesopotamia traced the same constellations that sailors navigated by centuries later, that poets wrote of, that children still stare at from the backs of cars on long summer drives. The sky above you tonight, whatever sky it is, cloudy or clear, city lit or rural dark, connects you to every human being who has ever lived. All of them looked up. All of them wondered. And tonight, we get to wonder too, gently, without pressure, without needing to remember a single thing. I'll share with you 100 facts about space, not to educate you, not to challenge you, but to give your mind something beautiful and vast and unhurried to rest inside. Think of it the way you might think of falling asleep to the sound of rain. The rain doesn't need you to count the drops. It only needs you to let it fill the room around you. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. Now then, let your shoulders soften just a little. If your jaw has been holding any tension today, let it loosen now. Allow your breathing to begin to slow of its own accord. Don't force it, just invite it. Let the day, with all its small urgencies and unfinished thoughts, begin to drift back from you like a tide going out. The stars are waiting, and they are, as stars always are, perfectly patient. Let's begin. The universe is approximately 13.8 billion years old. That number is so large that it resists ordinary comprehension, and perhaps that's exactly as it should be. When we try to hold a number like 13.8 billion in our minds, we can feel our thoughts begin to loosen at the edges, and that loosening is actually a kind of gift. The mind that cannot quite grasp something vast is a mind that has been invited to let go of its usual grip on things. And letting go, as you may be discovering right now, is very close to sleep. 13.8 billion years. If you were to compress all of that time into a single calendar year, one of those thought experiments that cosmologists love the entire history of human civilization would occupy only the last few seconds of December 31st. Every empire, every invention, every war, and every symphony, every single person who has ever lived all of it, compressed into moments that, on the cosmic scale, have barely had time to happen at all. And yet here we are. Here you are. Remarkable in your smallness, remarkable in the fact that you exist at all. The universe didn't have to produce anything that could notice it, and yet it did. The observable universe is approximately 93 billion light-years across. It's worth sitting with that phrase for a moment, the observable universe. Not the whole universe, mind you, but merely the part of it that light has had time to reach us from. The rest stretches on beyond what any telescope, any instrument, any eye could ever see. The observable universe is, in a sense, our neighbourhood, and our neighbourhood alone is 93 billion light years wide. A light year, in case the phrase is unfamiliar, is the distance that light travels in one full year, and light, moving at roughly 186,000 miles per second, covers enormous ground. In a single second, light could travel around the Earth more than 7 times. In a year, it crosses distances that make the imagination strain and then quietly give up, which is, as I say, entirely the right response. The strain followed by the giving up. That is what we're looking for tonight. Light from the sun takes about 8 minutes to reach the Earth. 8 minutes. That means that when you look at the sun, when you glimpse it setting on a warm evening, painting the sky in colours that seem almost too generous to be real, you're not seeing the sun as it is right now. You're seeing it as it was 8 minutes ago. You are in the most literal sense looking into the past. This is true of everything in the sky. The stars you see tonight are not the stars as they are in this moment. You're seeing them as they were years, decades, centuries, sometimes millions of years ago. The light left those stars long before you were born, and it has been travelling all this time through the silent cold of space to arrive precisely here, precisely tonight, to fall gently against your eyes. There's something quietly tender about that, if you allow yourself to feel it. The nearest star to our Sun is Proxima Centauri, about 4.24 light years away. At the speed of our fastest current spacecraft, which moves at roughly 35,000 miles per hour, it would take us about 73,000 years to reach Proxima Centauri. 73,000 years. The ancestors of modern humans were still largely living in caves 73,000 years ago. The gap between us and even our closest stellar neighbour is so immense that it simply cannot be crossed in anything resembling a human lifetime with the tools we have today. And there is something oddly comforting in that if you hold it the right way. The universe is not in a hurry. It has arranged itself at distances that remind us, gently but persistently, that vastness has its own kind of value. Not everything needs to be close at hand, not everything needs to be reached. There are more stars in the observable universe than grains of sand on all of Earth's beaches combined. This is one of those comparisons that astronomers reach for often, and with good reason, because it does something rather wonderful to the mind. We've all held sand in our hands. We've all felt it sift through our fingers on some beach or other, in some warm place, at some unhurried moment. And if you try, right now, to imagine every grain on every beach that exists on this planet, every shoreline, every desert of sand, every sandbar and seafloor, you find that your imagination strains and then, again, gently gives up. There are more stars than that, significantly more. Estimates suggest there are somewhere between 1 and 2 sextillion stars. That's a 1 followed by 21 zeros. Every one of those stars is a sun. Many of them have planets. Some of those planets, we now know, sit in what astronomers call the habitable zone, not too hot, not too cold, the right range for liquid water. You can do with that thought whatever you like. But it does seem to suggest that the universe is, if nothing else, extraordinarily generous with its materials. The Milky Way galaxy contains between 100 and 400 billion stars. We live inside it, which makes it difficult to see clearly, rather like trying to describe a house while standing inside one of its walls. What we know is that our galaxy is a great, slowly turning spiral, like a pinwheel viewed from above, with long arms of stars curving outward from a dense central hub. Our sun sits roughly 2/3 of the way out from the centre, on a quieter arm called the Orion arm, spinning around the galactic center at about 500,000 miles per hour. Even at that speed, one complete orbit of our galaxy takes about 225 million years. Astronomers have a name for this, a cosmic year, or a galactic year. The last time our Sun was in this same position in the galaxy, dinosaurs had only recently appeared on Earth. And the time before that? The first complex multicellular life was just beginning to stir in the ancient seas. We are, it turns out, new here. Even the Earth, ancient as it is, has only made it around the galaxy about 20 times. If your eyes are growing heavy now, that is perfectly fine. Let them close. Let the images continue to form behind them, the slow spiral of the galaxy, the distant light of 100 billion suns, and let yourself settle a little more deeply into wherever you're resting. There is nothing here that requires your eyes to be open. The universe will continue its slow turning with or without your watchful gaze, and it is entirely content to do so. Let your breathing find its own slow rhythm. Breathe in gently and out gently, and let the story carry on around you. The center of the Milky Way contains a supermassive black hole called Sagittarius, a star. It has a mass of about 4 million times that of our Sun, compressed into a region of space not much larger than the distance between the Earth and the Sun. It sits some 26,000 light-years away from us. Far enough that we're in no particular danger from it, which is reassuring, and it influences the motion of stars around it, the way a drain at the center of a pool influences the slow circling of water. Black holes are among the most philosophically interesting objects in the universe, because they represent a place where our ordinary understanding of physics, space, time, matter, light breaks down entirely. At the very center of a black hole is what physicists call a singularity, a point where density becomes infinite and the equations we use to describe reality simply stop making useful predictions. The universe at its extremes exceeds our ability to describe it. There is a kind of humility in that, a kind of permission to not know everything. Light cannot escape from a black hole. This is the property that gives black holes their name, and it is genuinely extraordinary when you pause to consider it. Like the fastest thing that exists, the thing that crosses 7 times around the Earth in a single second cannot, once it has passed a certain threshold near a black hole, find its way back out. That threshold is called the event horizon, and it is, in a sense, a point of no return. What happens beyond the event horizon is something we cannot directly observe, for obvious reasons. No signal, no information, no light can come back to tell us. And so the interior of a black hole remains one of the great mysteries of science, not because we haven't thought about it carefully enough, but because the universe has arranged things so that certain places are simply and permanently private. Think of it the way you might think of the inside of a dream. The images are there, vivid and real to the dreamer, but no one else can quite see in. Time passes more slowly near massive objects. This is a consequence of Albert Einstein's theory of general relativity, developed in the early 20th century, and it has been confirmed repeatedly by careful experiment. The closer you are to a massive object, a planet, a star, a black hole, the more slowly time flows for you relative to someone farther away. This isn't a metaphor or a philosophical position. It's a measurable physical fact. The clocks on GPS satellites orbiting high above the Earth where gravity is slightly weaker actually tick faster than identical clocks on the ground by about 38 microseconds per day. That doesn't sound like much, but GPS systems have to correct for it constantly. Your navigation would drift by miles within hours. Einstein's strange vision of time as a flexible, malleable thing something that bends and stretches depending on where you are, turns out to be practically important for finding your way to the grocery store. Space is almost completely silent. In the vacuum of space, there is no medium for sound to travel through. Sound requires matter, air, water, the ground beneath your feet to carry its vibrations. In the emptiness between stars, there is no such medium. A supernova could explode just beyond our solar system, releasing more energy in a few seconds than our sun will emit in its entire 10 billion year lifetime, and it would make no sound that any human ear could hear. This is worth imagining as you rest tonight. The universe, in its vast majority, is a silence so complete that no human being has ever truly experienced anything like it. The quietest room ever built on Earth, an anechoic chamber designed to absorb nearly all sound, still contains the sound of your own heartbeat, your own blood moving, your own breathing. True silence doesn't exist for us, but space has it. Space has a silence so perfect and so ancient that even our best instruments can't fully communicate it. The International Space Station orbits the Earth at about 17,500 miles per hour. At that speed, the astronauts aboard it experience approximately 16 sunrises and 16 sunsets every single day. 16 times they watch the sun rise over the curve of the Earth. 16 times they watch night sweep across the continents below. The ordinary rhythm of a human day, that reliable alternation of light and dark that has organized human life since the beginning, becomes something else entirely, something too fast to sleep by, too frequent to feel meaningful in the usual way. Astronauts aboard the station keep their schedules set to coordinated universal time, a kind of artificial day imposed on a situation where natural time no longer quite applies. They close the window shutters to simulate night. They follow routines built not from the movement of the sun, but from clocks and protocols and the simple human need for rhythm. Even in space, we reach for the ordinary. Even at 17,500 miles per hour, we need something to feel like home. The footprints left by Apollo astronauts on the moon will last for millions of years. The moon has no atmosphere, no wind, no rain, no weather of any kind. And so the marks left by 12 human beings who walked its surface between 1969 and 1972 remain there today, perfectly preserved, as clear and fresh as the moment they were made. Neil Armstrong's boot print, perhaps the most famous step in human history, is still there, on the Sea of Tranquility, waiting in the silence. It will still be there long after every building on Earth has crumbled, long after every word written in every language has faded, long after the cities and the roads and the farms and all the accumulated human tintin marking of this planet has been softened and erased by wind and rain and time. Those 12 sets of footprints will remain, patient and quiet in the lunar dust. There is something deeply moving about that if you allow it in. From space, the Earth looks blue. This is the famous observation of astronauts, and it never seems to lose its power no matter how many times it's mentioned. The planet, seen from a distance, is predominantly blue, the blue of the vast oceans that cover about 70% of its surface, softened by the white swirl of clouds, edged here and there with the brown and green of land. The astronaut Edgar Mitchell, who walked on the moon in 1971, described looking back at the Earth as an experience that produced in him an immediate, overwhelming, wordless sense of connection to the planet, to every person on it, to the whole of life. He said it felt like the universe was somehow knowing itself through him. That is, in its way, exactly what it is. You are the universe looking back at itself. Your consciousness, whatever it is and wherever it comes from, is the cosmos becoming briefly aware of its own existence. The atoms in your body were forged in the hearts of stars. The iron in your blood was born in supernovae billions of years before the Earth existed. You're not separate from space. You're made of it. There is no up or down in space. On Earth, gravity gives us an absolute orientation. Down is toward the center of the Earth, and up is away from it, and we organize our entire physical experience around this axis without even thinking about it. In space, away from any significant gravitational pull, that orientation disappears entirely. There is no floor and no ceiling. There is no reason to describe yourself as floating above anything or below anything, because those words lose their usual meaning. Astronauts on long missions report that this takes some psychological adjustment. The brain, which has spent a lifetime expecting gravity, keeps reaching for a floor that isn't there. After a while, though, something shifts, and space begins to feel simply like what it is: a vast, open, unoriented place where every direction is equivalent, where every position is simply where you happen to be. There's a kind of freedom in that if you can relax into it. The idea that no direction is more correct than any other, that where you are is exactly where you are. There is water in space, not just in the ice caps of distant planets or the geysers of Saturn's moon, Enceladus. Though those exist too, and we'll come to them. There is water vapour drifting in the clouds of gas that float between stars. There are vast molecular clouds in interstellar space that contain water, and in 2011 astronomers discovered a reservoir of water vapour surrounding a distant quasar, a brilliantly bright galactic core that contains 140 trillion times the amount of water in all of Earth's oceans combined. 140 trillion times the amount of water in all of Earth's oceans. The universe is extraordinarily wet when you step back far enough to see it properly. Water, the substance so essential to every form of life we know, is not rare or precious by cosmic standards. It forms wherever hydrogen and oxygen have a chance to meet and bond, which happens more often than you might expect in the chemical soup of interstellar space. Life, if it exists elsewhere, may have found its way there on a river that runs through the whole of the cosmos. It is worth pausing here for a moment. You're in no hurry, neither is this universe we're exploring together. If your thoughts have begun to soften at the edges, if the clear, sharp outlines of your day have started to blur a little, that is exactly right. That blurring is the beginning of something restful. Let it come. Allow your shoulders to drop if they've risen at all. Allow your hands to open a little, releasing whatever they've been holding. The facts will continue to arrive gently, one after another, like slow waves on a quiet shore. You don't need to catch them. You only need to let them wash over you. Saturn's rings are made mostly of ice and rock. They extend outward from the planet for hundreds of thousands of miles, and yet they are, in some places, only about 30 feet thick, extraordinarily thin relative to their vast breadth, like an enormous sheet of paper floating in space. If you could hold a piece of Saturn's rings in your hand, it would look like dirty snow fragments of ice ranging from tiny grains to chunks the size of houses, all drifting together in a slow, patient orbit. The rings are thought to be geologically young, perhaps only 10 to 100 million years old, which is relatively recent on a planetary timescale. They may have formed when a moon wandered too close to Saturn and was torn apart by the planet's powerful gravity. That shattered moon is now a ring. What was once a solid world became, in the unimaginable violence of its destruction, something breathtakingly beautiful. There is a thought in there worth holding gently. Jupiter is so large that all the other planets in our solar system could fit inside it. Jupiter's diameter is about 11 times that of Earth's, and its mass is more than twice the combined mass of all the other planets, moons, asteroids and comets in our solar system put together. It is not merely large, it is dominant, a gravitational presence that has shaped the history of our solar system in profound ways. Jupiter's immense gravity acts as a kind of cosmic shield for the inner planets. Its gravitational pull deflects and captures many of the asteroids and comets that might otherwise find their way toward Earth. Some astronomers believe that without Jupiter in its current position, the Earth would have been struck by large impactors far more frequently over its history, and the development of complex life might have been delayed or prevented entirely. We owe something to Jupiter, perhaps. We orbit in its gentle shadow, a little safer than we might otherwise be. The Great Red Spot on Jupiter is a storm that has been raging for at least 350 years. It was first clearly observed in the 1600s, and it has been churning continuously ever since a high-pressure storm system larger than the entire Earth, with winds that move at around 400 miles per hour. It is by any measure the most enduring storm in the solar system, a permanent feature of a planet where weather is not an interruption but a way of life. The Great Red Spot has actually been shrinking in recent centuries. When it was first studied carefully in the 19th century, it was roughly twice the size of Earth. It's now somewhat smaller than Earth, and some scientists believe it may eventually dissipate entirely, though what eventually means for a storm that has been ongoing for centuries is difficult to say. Even Jupiter's storms are patient. Even the most violent weather in the solar system has learned to take its time. Venus rotates backwards compared to most other planets. If you were standing on Venus and could see the sun through its thick clouds, which you could not, because those clouds are made of sulfuric acid and block almost all direct light, you would see it rise in the west and set in the east, the opposite of what we see from Earth. Venus also rotates so slowly that its day, the time it takes to complete one rotation on its axis, is longer than its year. A single day on Venus lasts about 243 Earth days, while a full orbit around the Sun takes only 225 Earth days. Venus is in many ways Earth's twin, similar in size, similar in composition, similar in distance from the Sun, and yet it evolved into a world of crushing atmospheric pressure and temperatures hot enough to melt lead, a hellish landscape entirely hostile to life as we know it. Scientists study Venus partly to understand what Earth might have become under different conditions, and partly as a reminder that small differences in a planet's history can lead to vastly different outcomes. Twins, it turns out, can diverge completely. Mars has the tallest volcano in the solar system. Olympus Mons rises about 13.6 miles above the Martian surface, nearly 3 times the height of Mount Everest above sea level. It is also extraordinarily wide, roughly the size of the state of Arizona, because Mars's lack of tectonic plate movement allowed lava to pile up in one place for millions of years, rather than being distributed along moving plates the way volcanic islands are on Earth. Standing at the base of Olympus Mons, you would not be able to see its summit. The volcano is so wide that the horizon curves away before the peak comes into view. You would be on the slopes of the largest volcano in the solar system without being able to see it. There's something almost philosophically useful in that the reminder that scale can make things invisible as easily as distance can. Mercury has the most extreme temperature swings in the solar system. Without an atmosphere to retain heat, the side of Mercury facing the Sun reaches temperatures of about 800 degrees Fahrenheit, while the night side drops to around negative 290 degrees Fahrenheit. That's a temperature swing of more than 1,000 degrees between one side of the planet and the other. Mercury is also a world of surprising paradoxes. Despite being the closest planet to the Sun, it is not the hottest. That distinction belongs to Venus, whose thick atmosphere traps heat so effectively that it maintains surface temperatures of around 900 degrees Fahrenheit both day and night. Mercury's proximity to the Sun gives it intense solar radiation, but without an atmosphere to trap that energy, the heat simply radiates back into space the moment the Sun goes down. There is a lesson somewhere in there about the difference between closeness and warmth. There are water geysers on Saturn's moon Enceladus. Enceladus is a small icy moon about 300 miles across, and yet it is one of the most scientifically exciting objects in the solar system. Beneath its frozen surface lies a liquid ocean of salt water, warmed by the tidal forces of Saturn's gravity, squeezing and flexing the moon's interior. And through cracks in the ice near its south pole, that liquid water is actively spraying out into space, enormous plumes of water vapor and ice crystals reaching hundreds of miles above the surface. The Cassini spacecraft, which orbited Saturn for 13 years before making its final plunge into the planet in 2017, actually flew through these plumes. And what it found was extraordinary. The water contains organic molecules, hydrogen gas and silica particles consistent with hydrothermal activity on the ocean floor. These are conditions very similar to the deep-sea hydrothermal vents on Earth, where life thrives in complete darkness, fueled entirely by chemical energy rather than sunlight. We have not yet found life on Enceladus. We have found all the ingredients. There is no air in space, but there is something. Space is often described as a vacuum, and it is, compared to anything we experience on Earth. But it is not perfectly empty. Between the planets, there drifts a thin stream of charged particles constantly flowing outward from the Sun, called the solar wind. Between the stars, there is a sparse scattering of atoms, mostly hydrogen and helium, at densities so low that a cubic inch of that interstellar medium might contain fewer atoms than the best vacuums we can create in a laboratory. And between galaxies, the intergalactic medium is even more empty, perhaps just a handful of atoms per cubic meter. But it is still, technically, something rather than nothing. True nothingness, it turns out, may not exist anywhere in the observable universe. Even the most apparently empty regions of space are threaded through with energy, with quantum fluctuations, with the quiet restlessness of matter at its smallest scales. The universe, it seems, finds emptiness somewhat difficult to maintain. Let's come to rest for a moment in that thought, the universe that resists emptiness. Even in the stillness you're moving towards right now, there is something. Your breath, moving in and out, the quiet rhythm of your heartbeat, the small warmth of wherever you're lying. Stillness is not nothingness. Rest is not absence. What you're moving toward right now is its own kind of fall. There is nothing you need to hold on to right now. Let your shoulders drop a little if they have risen. Let your hands settle. Let your mind begin to drift, as it wants to, out toward those quiet reaches of space where the only sound is the one you're not quite hearing. The Hubble Space Telescope has photographed light from galaxies more than 13 billion light-years away. The Hubble Ultra Deep Field, an image created by pointing the telescope at a seemingly empty patch of sky and collecting light for over 11 days, revealed approximately 10,000 galaxies in a region of sky that appeared completely blank to the naked eye. 10,000 galaxies, each containing hundreds of billions of stars, in a speck of sky smaller than a grain of sand held at arm's length. Every direction you look in the night sky, Behind every apparent gap between visible stars, there are galaxies beyond count. The universe is not mostly space. In a sense, it is mostly galaxy, mostly star, mostly light. The darkness we see from Earth is an illusion of scale. What looks empty is, at deeper depths of field, absolutely teeming. Some stars are so large they would swallow our entire solar system. The star known as VY Canis Majoris. A hypergiant in the constellation Canis Major is so enormous that if it were placed at the centre of our solar system, its surface would extend beyond the orbit of Saturn. Saturn, which orbits the Sun at nearly 900 million miles, would be inside this single star. Our own Sun is not a small star. It contains 99.86% of the total mass of our solar system, and Earth could fit inside it about 1.3 million times. But beside a hypergiant, our Sun is a modest thing, a quiet yellow dwarf going about its business in a mid-range arm of a mid-range galaxy, sustaining one small blue planet with warmth and light. There is no shame in being the quiet one. A neutron star is so dense that a teaspoon of its material would weigh about 1 billion tons. When a massive star reaches the end of its life and collapses under its own gravity, the result, if the star isn't quite massive enough to form a black hole, is a neutron star, an object roughly the size of a city, perhaps 12 miles across, but with more mass than our Sun. The gravitational collapse is so extreme that protons and electrons are forced together to form neutrons, packed with a density that defies ordinary comprehension. That teaspoon of neutron star material, weighing 1 billion tons, would instantly fall through the floor of any room on Earth, through the bedrock beneath, through the mantle and the core, and come to rest at the very centre of the planet. It would take a while, but it would get there. The universe contains objects of such extraordinary density that the matter we're made of, the stuff that feels so solid when you press your hand against a wall, would simply cease to behave the way matter normally behaves in their vicinity. We are made of surprisingly empty space ourselves, of course. The atoms that make up your body are mostly void. The electrons orbiting each nucleus are so far from it, proportionally, that if an atom were the size of a football stadium, the nucleus would be the size of a pea at the centre. What feels solid is an arrangement of forces and fields that creates the experience of solidity without being, at its most fundamental level, solid at all. You're something remarkable and strange and mostly empty, resting in the dark. Some stars pulse. There is a class of star called a Cepheid variable, which expands and contracts in a remarkably regular rhythm, brightening as it expands, dimming as it contracts, over periods ranging from a few days to a few months. These pulsations are precise enough that astronomers use them as what they call standard candles, objects of known brightness that can be used to measure distances across the universe. The astronomer Henrietta Swan Leavitt discovered the relationship between the pulsation period and the luminosity of Cepheid variables in 1908, working as a human computer at the Harvard Observatory, one of a group of women hired to analyze photographic plates of the sky. Her discovery fundamentally changed our understanding of the scale of the universe, providing the first reliable way to measure distances to other galaxies. Edwin Hubble later used her work to demonstrate that the fuzzy patches in the sky that astronomers had been calling nebulae were, in fact, entire galaxies millions of light years away. Henrietta Leavitt never received the recognition she deserved during her lifetime, but the universe she helped us see more clearly has not forgotten the work. The universe is expanding, not just in the sense that galaxies are moving away from each other through space, but in a more fundamental sense. Space itself is stretching. The fabric of the universe is expanding, carrying galaxies along with it the way raisins in a rising loaf of bread are carried apart from one another, not by any motion of their own, but by the expansion of the dough between them. Edwin Hubble observed in 1929 that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This was the first direct observational evidence that the universe is expanding, which means, by working backward in time, that everything must have once been much closer together. Close enough, if you go back far enough, to be contained in a single point of almost infinite density. The Big Bang is not quite the explosion it's often described as. It is better imagined as the moment when the expansion itself began, when space and time started, when the story opened its first page, when the universe began its long and patient unfolding. The expansion of the universe is accelerating. In 1998, two teams of astronomers independently discovered something that surprised even them. The universe is not only expanding, but expanding faster and faster over time. Something is pushing the expansion, counteracting gravity over vast distances, causing the universe to stretch at an increasing rate. That something, whatever it is, has been given the placeholder name dark energy. It accounts for approximately 68% of the total energy content of the universe, the dominant substance, if it can be called that, of everything that exists, and we have essentially no idea what it is. It doesn't interact with matter or light in any way we can detect. Its existence is inferred entirely from its effect on the motion of galaxies. About 27% of the universe is dark matter, another mysterious substance that we know exists because of its gravitational effects, but cannot directly observe or detect. And ordinary matter, the stuff of stars, planets, rocks, air, water, and everything you have ever seen or touched, makes up only about 5% of the universe. We live in a universe that is, by a significant majority, made of things we do not understand. Which brings us gently to the question of what we do understand. We understand that there are patterns. We understand that the same physical laws that govern the motion of planets also govern the behavior of atoms, that the equations work the same way in every direction, in every galaxy, at every point in time we've been able to study. The universe is, at a deep level, consistent. It follows rules. And even when we discover that we don't fully understand those rules as we do, regularly the discovery of our own ignorance has always, in the history of science, been the first step toward understanding something more. We've been wrong before, and been wrong in ways that led us to be more right. There is something patient and trustworthy about that process, even when individual discoveries feel sudden or surprising. There are billions of potentially habitable planets in our galaxy alone. Since the launch of the Kepler Space Telescope in 2009, astronomers have confirmed the existence of thousands of planets orbiting other stars, exoplanets they're called, and surveys suggest that nearly every star has at least one planet, and many have several. Of these, a significant fraction orbit in the habitable zone, that range of distances from a star where liquid water could exist on the surface. The Milky Way alone may contain tens of billions of such planets. Tens of billions! And that's just our galaxy, one of perhaps 2 trillion galaxies in the observable universe. The question of whether life exists elsewhere is one that science is actively working to answer, slowly and carefully, with the tools we have and the tools we're building. We don't know yet, but the odds, if you're the sort of person who thinks about odds, seem to be doing something interesting. The first confirmed exoplanet was discovered in 1992. For most of human history, the existence of planets around other stars was a matter of philosophy and speculation. Reasonable to imagine, impossible to confirm. Then, in 1992, astronomers detected 2 planets orbiting a pulsar, a rapidly rotating neutron star, by observing tiny changes in the timing of its radio pulses. The planet's gravity was tugging on the pulsar, creating infinitesimal variations in the regularity of its signals, and those variations were detectable. We found other worlds by listening for the whisper of their gravity. The first exoplanet confirmed around a sun-like star came a few years later, in 1995, 51 Pegasi b, a large, hot planet orbiting its star at a tiny fraction of the distance from Earth to the Sun. Since then, the catalogue has grown to thousands of confirmed planets and thousands more candidates in every conceivable configuration. Planets orbiting 2 stars at once, planets with rings, planets covered in oceans, planets of iron and lava, planets in perfect resonance with each other, their orbital periods maintaining precise mathematical ratios through the delicate choreography of gravity. Some exoplanets have 2 suns. The planet known as Kepler-16b orbits 2 stars simultaneously, a binary system where both stars are smaller than our Sun, gravitationally bound to each other, and together they are orbited by a gas giant about the size of Saturn. From the surface of that planet, if such a thing were possible to stand on, which it isn't, being a gas planet, you would see 2 suns rise, 2 suns set, 2 shadows stretching away from you in slightly different directions. Astronomers sometimes call such worlds Tatooine planets, after the fictional world in Star Wars where Luke Skywalker watches twin sunsets from the desert, longing for something beyond the horizon. The fictional image, it turns out, was not imagination but modest prediction. The universe was already doing this, patiently and without fanfare, long before anyone thought to write it down. There is a planet where it may rain glass. HD 189733b is a deep blue gas giant orbiting very close to its star, only about 63 light-years from Earth, close enough, in astronomical terms, to study in some detail. Its temperature is around 1,700 degrees Fahrenheit, and its winds are measured at roughly 5,000 miles per hour. The bluish colour comes from silicate particles in its atmosphere, tiny shards of what amounts to glass, suspended in the screaming winds and occasionally raining sideways at several times the speed of sound. It is, by any earthly measure, a terrifying world. And yet there is something oddly beautiful about it too, the way it takes ordinary materials, silicon and oxygen, the stuff of beach sand and window glass, and transforms them into something so extreme that only mathematics can fully describe it. The universe has a tendency to take familiar ingredients and do completely unexpected things with them. We are perhaps one of those experiments. The Voyager 1 spacecraft, launched in 1977, is now more than 23 billion miles from Earth. It is the most distant human-made object in history. It crossed the boundary of our solar system, the heliopause, where the solar wind finally gives way to interstellar space in 2012, and it has been drifting through interstellar space ever since, sending back faint signals that take more than 20 hours to reach us, even travelling at the speed of light. Voyager 1 carries a golden record, a copper disc covered in gold, containing sounds and images selected to represent the diversity of life and culture on Earth, along with instructions for playing it. It carries greetings in 55 languages. It carries music Bach, Beethoven, a Pygmy Girl's initiation song, Chuck Berry's Johnny Be Good. It carries the sounds of wind, rain, surf, crickets, birds, a mother's first words to a newborn child. It is out there right now, in the darkness between stars, carrying the sound of Earth. There is something about that small and vast at once that is very difficult to put into words. Allow your breathing to find its own slow rhythm as we continue. You don't need to hold on to any of these images too tightly. Let them come and go the way light passes through a window present, luminous, and then gently moved on. The Voyager spacecraft is out there in the dark. The glass rain is falling sideways on a blue planet 63 light-years away. Enceladus is quietly spraying its ocean into space. And here you are, warm and still, at rest. Let the images soften a little at the edges if they want to. Let them become impressions rather than facts, feelings rather than figures. Let the universe be vast and quiet around you while you settle into something smaller and closer and warm. The sun produces more energy in 1 second than humanity has used in its entire history. The sun generates energy through nuclear fusion, a process in which hydrogen atoms in its core are fused together to form helium, releasing enormous amounts of energy in the process. The core of the sun reaches temperatures of about 27 million degrees Fahrenheit, and under those conditions, roughly 600 million tons of hydrogen are converted to helium every single second. Every second. 600 million tons. The light and heat that result from this process take about 100,000 years to travel from the core of the sun to its surface, bouncing and reabsorbing through the dense plasma of the solar interior in a long random walk. And then, once they finally reach the surface, they cross the remaining 93 million miles to Earth in just 8 minutes. The sunlight warming your face on a summer day left the center of the sun before modern humans existed. Our sun is in the middle of its life. It formed about 4.6 billion years ago from a collapsing cloud of gas and dust, and it's expected to continue burning in its current stable phase for another 5 billion years or so. After that, it will gradually expand into what astronomers call a red giant, swelling outward as its core fuel is depleted, potentially engulfing the inner planets. Eventually, it will shed its outer layers, leaving behind a small, dense remnant called a white dwarf. 5 billion years is an almost unimaginable amount of time, but stars, for all their enormous power, are themselves mortal. Every star we see in the sky is somewhere on its own arc of birth and life and eventual ending. The universe contains stars in every stage of this process, newly forming stars in vast gas clouds called nebulae. Mature stars like our sun, old and swelling red giants, and the remnants of stars that have already completed their journey. A sky full of stars is a sky full of life stories, each at a different chapter. Nebulae are the birthplaces of stars. A nebula is a vast cloud of gas and dust in interstellar space, sometimes hundreds of light years across, where new stars are slowly forming. Under the influence of gravity, small regions within the cloud begin to collapse inward, the material gathering and compressing until the core becomes dense and hot enough to ignite nuclear fusion. A star is born. The Orion Nebula, visible to the naked eye as a faint smudge in the sword of the Orion constellation, is an active stellar nursery containing hundreds of young stars in various stages of formation. Images from the Hubble Space Telescope show it as a gorgeous, billowing cloud of glowing gas, lit from within by the energy of newly born suns, sculpted by stellar winds into shapes of extraordinary delicacy and beauty. When you look at the Orion Nebula, you're watching the same process that created our own sun happening again in real time. Stars are born in clusters, Stars don't usually form alone. They form in groups, sometimes dozens, sometimes hundreds of thousands of stars, emerging from the same cloud of gas and dust at roughly the same time, sharing the same origin and the same early neighborhood. These groups are called star clusters, and they gradually disperse over millions or billions of years as each star follows its own orbital path through the galaxy. Our Sun was almost certainly born in a cluster too long ago. Over the 5 billion years since its formation, the other members of that original family have scattered across the Milky Way, now too far apart to recognize each other as siblings. There are stars out there, somewhere in our galaxy, that formed from the same cloud as our sun sister stars in a sense, that shared our solar origin. We have siblings in the galaxy. We just don't know where they are. The moon is slowly moving away from Earth. Every year the moon drifts a little over an inch further from us. It's a consequence of the tidal interaction between the Earth and moon. The ocean tides raised by the moon's gravity transfer energy from the Earth's rotation to the moon's orbit, gradually pushing it outward. As the moon recedes, our days are also slowly getting longer. The transfer of energy is gradually slowing the Earth's rotation. In the very ancient past, the moon was much closer, the days much shorter, the tides far more dramatic, and in the very distant future the moon will be farther away and the tides gentler. We tend to think of the night sky as fixed and permanent, the same moon that has always been there, exactly where it has always been. But everything is in motion. Everything is slowly, patiently changing. The moon is leaving a little bit every day, and the Earth every day is letting it go a little more. Moonlight is sunlight. The moon produces no light of its own. What we call moonlight is sunlight reflected off the lunar surface, which is not particularly shiny, being made of dark volcanic rock. The moon reflects only about 12% of the sunlight that strikes it, and yet that reflection is enough to cast shadows on Earth, to illuminate entire landscapes with a cool silver light, to make the world look different from how it looks in daylight, softer, stranger, more mysterious. Every poem ever written about the moon, every legend, every story, every sleepless night spent lying awake watching it move across the sky, all of it was inspired by borrowed light, by the sun's light, gentled and slowed and cooled by the long journey from star to rock to Earth, by reflection. Sometimes what reaches us is not the original thing, but something that has been shaped by the journey. And sometimes that reflected, travelled, gentled version is exactly what we needed. There is a point between the Earth and the moon where the gravitational pull of each body is equal. It's called the L1 Lagrange point, and it sits about 326,000 miles from Earth. At that point, the pull of Earth's gravity and the pull of the moon's gravity are exactly balanced. An object placed there with no other forces acting on it would remain in equilibrium, belonging equally to both bodies and to neither. There are 5 such Lagrange points in the Earth-Moon system, and they have practical uses. Some telescopes and spacecraft are positioned at Lagrange points to maintain stable orbits without expending fuel.